The world of mathematics can be very unpredictable at times. Sometimes, to solve certain problems, we need to understand the hidden structures behind them. For example, let's look at this problem. So, find the limit when x goes to 0 plus ln x plus 1 of x. So there's one comment that I want to make. Sometimes when you write these problems, you do not write the parentheses around. But if you do not write the parentheses, that problem is a completely different problem because the limit only belongs to the term right next to it. So make sure that you put parentheses around for the to express what you really want. Okay, anyway, so let's go back to the problem. So we have limit x goes to 0 plus ln x plus 1 of x. But when you look at this problem, it looks like a adding problem. So the adding problems are not like, we are not used to, like we don't say this is like a Bernoulli problem, because we normally have like a infinity minus infinity and situation like that. But let's actually look at what really going on here. So if you look at the graph of ln x, and you can see that it's gonna go like that. So when it goes to 0, you can see when it goes to 0, you can see the function goes to negative infinity. So ln x goes to negative infinity when x goes to 0 plus. So that means the first term goes to negative infinity. Also look at the second term. So what is the graph of the second term? So if you look at the, so we know this is 1 over x, the rectangular hyperbola. So that means the graph gonna look like that. That's like one side, this is the other side. So that's the shape of the graph. This is like how 1 over x looks like. That means when x get bigger, value get smaller. When value gets smaller, x get bigger. So interesting. So that since x going to 0 through larger values, that means the function goes to infinity. So second was infinity. So that means this is actually an infinity minus infinity problem. So that means we can solve this one using the type 3 of the Bernoulli's method. So if you are not familiar with the type 3 Bernoulli, and you can look at the, you can study that, the link is in the description. So let's try to solve the problem now. So what we have limit x goes to 0 plus ln x plus 1 of x. So that means what we normally do if you get a problem like infinity minus infinity problem, under type 3, what we normally do, we do the algebra first. So that means we can simplify this. So limit x goes to 0 plus. So let's simplify this one. So this one, that's not difficult to simplify. What we normally do is we can put a 1 here. So we use a 3a argument. So if you don't know what's a 3a argument, again, there's a link in the description to understand what's going on here. So we're going to multiply like arrows. So we're going to multiply this way and multiply that way. And multiply this. That's a 3a. There are 3 arrows. Okay, so let's do that. So if you do that, what will happen is first you get x ln x. That's the first term. The second term is 1 times 1, which is 1. The denominator you get 1 times x, which is x. So that's what you get. So now when you look at this problem, it may not be clear yet because the bottom is very clear, that's going to go to 0. But what about the top? So to understand this part, so what we can do is actually you know like this limit. This is like a limit that we found in the type 2 problems. So this is like infinity times 0 problem. This is infinity times 0 problem. So again, you can find more like that in the type 2 video, Bernoulli type 2 video. So if you are not familiar with that problem, let me do it right here. So let's do it. So we have limit x goes to 0 plus, we have x ln x. That's what we have. And you can see that x goes to 0, ln x goes to negative infinity. So it's a 0 times infinity problem. So if you have 0 times infinity problem, what we do, we're going to convert that into type 1. Type 1 means either 0 or infinity or infinity. So what we normally do, the easiest way to do this problem is you're going to divide the top and bottom by x. So that means it's going to be x to the negative 1. Now once you do that, you can clearly see this is a the top is infinity, negative infinity, bottom is also infinity. So because 1 over x, x goes to 0, 1 x goes to infinity. So now that means we can use the Bernoulli type 1 now. So if you use the Bernoulli type 1, that means you just take the derivatives. If you take the derivative, what will happen? This get 1 over x. the bottom get negative x negative 2. So that's the derivatives, and then what we do, we simply use the algebra now. The easiest way to continue with this problem is just multiply the top and bottom by x squared. That's the easiest way to do this. So if you do that, and you can see, you can pull the negative sign out, limit x goes to 0 plus, so you can see the top simply going to be x, the bottom going to be 1 actually. So you can see when you multiply these two, you get 1. So you don't write it. Now what will happen when x goes to 0 plus, this term goes to 0. That means the limit when x goes to 0 plus, xl in x actually goes to 0. So you can mark that now. So if you go to the problem, you can see the term here, this term goes to 0 as x goes to 0 plus. So that means what will happen if you look at the original limit, so it's a limit x goes to 0 plus, the top goes to 1 now, the bottom is x. So that means since x goes to 0 plus, what will happen is it is 1 over 0 plus. What is 0 plus means? It's not 0. You know that you cannot divide by 0, but you can divide by 0 plus. Because 0 plus is not a number. It's like something approaching 0 through positive values. That's what it means. So if they happen, so you get positive infinity. So the answer is positive infinity for this problem. So it's very interesting. So you can see it doesn't look like a Bernoulli problem at the beginning, but when you do the algebra, when you do the math, and you can see this end up with positive infinity. Let's look at another one just to see how things can go. Let's say we have x goes to 0 plus ln x plus cotan x. So ln x is the troublemaker here. So again, if you look at the two graphs, we know the ln graph from the previous one. So I'm just going to repeat it just for completeness. So when you go to 0 plus, this goes to negative infinity. So first term is negative infinity. That's all right. But the second term, so again, this doesn't look like a Bernoulli problem with a plus sign. But let's see what happens to the cotangent function. Cotangent is 1 over tangent. So we know that the tangent goes to 0 when x goes to 0. So that means this can go to infinity on this side. Here it's going to go to infinity, and this is going to go to negative infinity. So that part is clear. And then also they have asymptotes. So we have these asymptotes because when this goes to infinity, there was asymptote for the tangent, but now it become a, because 1 over infinity is 0. So that means it's going to go like this and going to go like that. So the asymptote is over there now. And the same thing happened here. So you can see there's asymptote over there. So that means it's going to go like this. So that's the graph of cotangent. This doesn't look like good. So this is the graph of cotangent. So now you can see when x goes to 0, this side goes to positive infinity. So that means the second term is positive infinity. So it's again a infinity minus infinity problem. So that means this is again Bernoulli type 3. So how we do it type 3? We use algebra. That's the trick. We use algebra to simplify first. So it's a limit x goes to 0 plus. So we have we can write this one as actually ln x plus 1 over tan x, with cotan is 1 over tan. Now again we use a 3-arrow argument. So what will happen is, you can see this is going to be ln x tan x plus 1 divided by, this is like, you can write this one as a ln over 1, that's very clear, and then tan x. Okay, that's what you get. So now the problem is, we don't know what's going to happen to this term. So you can see when x goes to 0, the first term goes to negative infinity, the second term goes to 0. It's a 0 times infinity problem. That means a type 1 Bernoulli. So how we do it? We're going to convert. So let's do, I'm going to do it over here. So it's a limit. X goes to 0 plus tan x ln x, which is, you can write as a limit x goes to 0 plus ln x. What I'm going to do, I'm going to bring the tan term to the denominator, so you can write this one as cotan x when you bring it to the bottom. It's a 1 over. Now you can see right after you do that, because earlier it was a 0 times infinity problem, but right after we do that, now you can see it is an infinity over infinity problem. So we can take the derivatives now. So if you take the derivatives, so you can see derivative of the top is 1 over x, that we know. Derivative of cotangent. Cotangent means there's a negative sign because there's a c, that means there should be negative. Cotangent means cosecant squared. So cosecant squared x, that's what you get. Now what we're going to do, we can actually do some nice algebra trick here. We can move the terms around. So we can say limit x goes to 0 plus, what I'm going to do, I'm going to multiply the top and bottom by sine squared. So then the bottom get cancelled out because the cosecant is 1 over sine. So it's going to be sine squared x. And then also you're going to multiply the top and bottom by x. So that means x get cancelled from the top, you get to go to the bottom. Now what we can do is we can split this. So if we split this, you can see it is x goes to 0 plus, you can write this one as sine x over x times sine x. Or if you do not like that method, you have another way to do this problem actually. So this is one way to do it. Let's do this in a different way. What I'm going to do, you notice that this is again a type 1 problem. You can see this is a 0 over 0 situation. Since this is 0 over 0, it's a type 1, that means you can basically take the derivative. That's actually much quicker. So you can see when you do that, the top going to be by the chain rule 2 sine x, take the derivative of the inside function which is cosine x, the bottom is just 1. Now what will happen when x goes to 0 plus, you can see this term goes to 1, this term goes to 0, that means the whole product goes to 0. So that's like a quick way to do it. You can also do the previous method, but this is much quicker. Okay, so now it's 0, so that means the limit of that term is 0, that means we can put it there. So this is 0, this goes to 0. So that means what will happen, this problem will be very similar to the previous problem that we did. So the top goes to 1 and the bottom goes to is a 10. So 10, you can leave it like 10, or you can even convert to cotangent. But even if you argue with tangent, meaning that when x goes to 0, tan goes to 0, positive 0. So that means this is going to go to positive infinity. So again, answer to this problem is also positive infinity. So this is what happens. So there are certain problems like that. Those are like hidden problems, what we call hidden Bernoulli problems, and you need to kind of understand what's going on. So you kind of look at how the graph may look like. I want to show you one more example. Let's look at this one. So we have limit x goes to 0 plus ln x minus 1 over x. This is actually, when you look at, apparently it looks like it's a Bernoulli problem, but it's not. It's not a Bernoulli problem. Let's look at the graph. So we know those two graphs. The first one is this one. So it goes to negative infinity when x goes 0, so it's negative infinity. And again, what will happen to the other one? Other one also, we know the graph of that one. That looks like this rectangular hyperbola. So again, if you go to 0, you can see this goes to infinity. So that means so here it's going to be infinity. So this is a infinity minus infinity problem. Why minus? Because there's a negative sign here. So it's infinity minus infinity is not indeterminate form. We know exactly what this look like. So that means infinity minus infinity means minus infinity. So this one you can use the Bernoulli for this problem, because this is not the indeterminate form. This is, we know this exactly goes to negative infinity. So please don't fall in these pitfalls. So there are few things that you really need to understand when you do work with Bernoulli problems. Okay, so I hope you learned something here. So thank you so much for watching.